some sense, only the pieces of information that are useful to us. And this is, of course, a very delicate statement, because what do you mean by useful and what do you mean by filter the information? But I claim that eventually there is some optimal cycle of flow of information in this cycle. And this is actually, in cognitive science, this is really called the perception-action cycle. And it's really defined by other people as this flow of information, this cycle. And what I'm interested in is really what is the optimal cycle, in the sense of most efficient, in the sense of getting exactly the right information and only the right information in order to be valuable in your behavior. So this is really a picture which I like very much, because it tells me there are actually two channels here. And these two channels have to be balanced if I'm thinking about an ongoing quasi-stationary activity like what we are doing now. I'm speaking and you are more or less understanding what I'm saying, and there's some sort of flow of information between us, and during the next few minutes it's going to be quasi-stationary. There's not going to be high fluctuations, I hope. But of course, here and there are. And we know, of course, we heard it actually more or less from Merav yesterday, that our brain is also largely divided between the frontal and the dorsal, or how do you call it, parts of the brain. The frontal part, the red part here, which is really highly developed in humans, mainly because we are planning ahead further than any other animal that we know. But it's not only this. It's really dealing with what we call the executive functions. I mean, motor control, planning, making decision. Merav emphasized yesterday the decision making, the comparison with. But actually, it's much more than that. It's all the things which are, in some sense, future looking. Whereas the dorsal part, especially the visual V1, which is right there in the back of our occipital cortex right here, is dealing with sensory perceptions. And the brain is really, the cortex is really nicely divided very sharply in an area called the sensory motor, or this particular motor map of the brain, which we have exactly side by side, the perception part and the active part, which actuates and receive the muscles that really activate, other than there's some sort of a distorted map of our body on this region on both sides. So this is really interesting to note that even the cortex, which is not the primary player of this game, is very nicely divided, and we really have this interesting flow of information. And as you could see in the previous slide, this is not one flow, it's actually, yes, there are multiple cycles or multiple time scales. So the sensory motor cortex has time scales of milliseconds, essentially. I mean, within 50, 100, 200 milliseconds, I sense the environment and I respond to it. And the further we go, or to longer and longer cycles, we have further into the past and further into the future planning and perception. So this is really important. So this brain is really a multiple cycle machine which really processes information in such flows on multiple scales. And what is really crucial to understand this picture, and this is where we start to differ, is the notion of past and future, or what we called yesterday causality. All right, so this is how I believe and how many believe today that this is really the central goal of the brain, process information in this cycle. So this is directly related to the model that Eli mentioned very briefly yesterday. We think about the brain as some sort of a cyclic machine, or if you want, channel with feedback, where the perceptual information is moving by collecting all sorts of objects from the past of the environment, and eventually filter it and get out of it just the relevant part, and then use it to make predictions and to plan your actions properly. So this is, and what is really interesting and very important in this game is that we have feedback here. Essentially, our senses can perceive, or can see, or can sense the action. So it's not a coincidence, for example, that the eyes and the hands are very nicely coordinated. As you can see exactly the hands at the right distance, and the resolution of the fingers is such that we can manipulate the finger exactly at our best sensory perception, visual perception. It's not a coincidence that our ears are tightly coupled with our voice, with our mouth voice production mechanisms. They are exactly coupled because they co-evolve, they evolve together to match each other, and so on. So this type of matching is due to the field, due to the fact that there's information in the future, in some sense, that we can, there's a channel that gives us information from the future to the past. This is what I call the predictive information, or the predictive channel of the environment. Without this channel, without the fact that there is information in the past about the future, we could not work, we could not operate. Actually, this ability to predict is essential for our existence. If you don't believe this, I can invite you only to take a whole course about it, which we give on the second semester. Now, of course, this is not only information. The main part of the story is that our actions have value. What do I mean by value? I can gather food, I can collect intelligence, I can by predicting the environment, the future, I actually learn something about the future and use it. And use it means that I can invest in the stock market and get the money, or I can play chess better and know what, if I have some prediction of what my opponent is going to do, I can win, and so on and so forth. And so when you think about it, everything around us is based to some extent on predictions. I mean, so this basketball player should know where the laws of physics well enough to know what's going to happen and where her friend is going to be when she throws the ball, and so on. The chess player, of course, has to then have anything that if you really think about it, is based on this ability to do something now which will be useful in the future. So the ability to predict is, for me, the most essential and better characterization of life that actually I think I can define life to some extent by this unusual ability to exploit the predictability of the environment. Without this, we are not alive. I mean, even bacteria, even viruses, very simple, very primitive creatures, you call them alive if they are somehow not entirely causal in the sense that their initial conditions predict their future. At least on some time scale, they behave as if they plan, as if they have some information about the future and they're going to use it. This is really very fundamental. So this is why I believe understanding this cycle is really critical, and that's want to get back to visual perception. So again, when we have this fundamental riddle, how is it that this collection of gray pixels are perceived somehow in our brain as dog and man and whatever, trees? How is this happening? And this is happening essentially by what used to be the canonical model of vision. Let's say Mars view of vision was some sort of a bottom-up flow. I mean, so the pixels are processed and then small features around the process, around the pixel of process and so on. So and actually the hierarchy of the visual system, V1, V2, V3, and so on, seems to support this. I mean, we start from very simple features, and then eventually we get to much higher elements. We now know that this is simply impossible on a computational basis. What actually happens, as Arno actually said yesterday, is that we somehow know that there is a dog before we see it. There's a bottom-up, where there's a top-down hierarchy, which is actually coming from the famous work of Merab Achisar that I was hoping she will mention, but it's too old for her. Anyway, it was actually predicted theoretically by John Tossos in around 1990, where he really examined the complexity of vision and came to the striking conclusion for me that vision, this bottom-up processing of Mark cannot be true. Simply not enough time. Even if we think that it's not only not enough time, this is the highly non-tractable, it's NP complete in the context of computer science, just this bottom-up processing from simple features to complex features. This cannot be the right way to vision. There must be something else, which actually is top-down, which presumes or predicts or hypothesizes what is there first and then verifies, because we know that hypothesis testing is a lot more efficient than unsupervised generation of objects. Anybody in machine learning knows it very well. Discriminative learning, or first guess and then test, is infinitely more effective. I need only very few tests of this dog, let's say ears, nose, color, size, so on. Very few facts can verify for me with very high probability that this is a dog But if I had to generate a dog out of all possible objects that could be there, this is a non-practical task computationally. And of course, several years later, around 2002, Merava Chisar with Charles Hochstein in her PhD actually verified this, or conjectured it independently actually, but they realized that there is this reverse hierarchy, that we react first to the large object, and without actually noticing at all the details. So if I blink a picture to you and ask is there a face there or not, you'll see the face before, without being able to tell me what was the color of the pixel on the left and so on. You first see the last things, and this is part of this process of guessing, testing, hypothesizing, guessing. So there is perception is about predictions. If you don't believe me, that we see what we expect to see, these are two famous examples. If I don't tell you, those, of course, many of you have seen it before, but if I don't tell you what is there, those who haven't seen it usually have absolutely no idea. Or what is here, what do you see here? So those who know it, most people who haven't seen it before see mountains and all sorts of things like this. And if I just tell you nude, you'll immediately see something else. Or something, I mean, I don't know if you see it, but you should see it. But especially the men here. But, so this is one of those very cute examples. This is, of course, a Dalmatic dog in somehow oblique or covered in this background, black and white background. But of course, when you know there is a dog, you see it. When you know this is the back of the nude, you see it immediately, and so on. So, and I claim this is not an unusual example. This is what's actually happening in our brain all the time. We first guess and then test. This is so much more efficient, especially if you think about optimizing this cycle. All right. So this is more or less the introduction. So how do we do it? I mean, so we need a simple, or at least in principle, simple model of representing this trade-off between perception and prediction. By the way, I know there are some people here from the intelligence. I won't tell you which one, but this is actually the fundamental problem of intelligence: which part of information in the past to use and how to collect it, how to filter the things that we don't need. And so it's not only fundamental for intelligence; it's the fundamental problem of our perception, our being as living creatures. So essentially, the story is very simple. If I want to formulate it mathematically, there's this river that never repeats itself, of flow of events from the past to the future. This flow of events, using this nice slides of Jonathan Rubin that I'm always using because it's the nicest demonstration of it, is some sort of flow. Okay, so as I said, I mean, it's not completely unpredictable. There is structure in the world. Actually, when we say that we cannot predict the future, we all lie. Because without predicting the future, we could not do anything. When I move my feet here and step on and I know that there is a floor here, and I know that you're going to be here in 10 seconds, more or less in the same shape, and so on and so forth. I mean, we always make prediction. We know that the sun is going to rise tomorrow. We plan ahead, actually, because most of the important things are predictable. It's only those tiny things which are surprising, which we really want to be able to predict better than others. But our complex environment, I mean, the fact that we have houses around us, and it's because we want to be protected against the fluctuations of the weather. If we put clothes, because we want to, for the same reason, and so on and so forth. So everything around us is behaved in a way to improve our predictability. So this is what I called before the feedback channel, and our poor internal representation, our poor creature, is actually trying to make sense of past information in a way which will be useful, and useful in my sense is predict the important parts, the valuable parts of the future. So how do we do this? So essentially, once I tell you this is what we want to do, we want to compress the past in the most efficient way, throw away everything that we don't need in order to use it correctly in the future. All we need to do is to formulate it mathematically. So there's some internal representation. Yesterday it was denoted by X hat, or I don't know what. And all sorts of notations here. There's some past, and I want to use this channel in a way that will allow me to make all the useful predictions in the future. Now, from here on, a lot of you know the story. So we think about it probabilistically. We think about the past and the future as some joint probability. So if you remember, again, Ellie's lecture yesterday that we had a sequence of sounds. And otherwise, so we actually knew, because he prepared the experiment that way, we knew the joint distribution of the past and the future. And from this joint distribution, but of course this is not something that the intelligence people know, but in experiments in our lab, we can know, or we know something. For example, in Daphne's talk, if you remember the last talk yesterday, I'm sorry that I refer to it, but I assume that some of you remember it. There was an explicit model of how this behaves, which is this Dirichlet process model that allows us. It was an explicit assumption about the way environments are generated. There was no temporal aspect there, but it actually was implicit in this Bayesian assumption. Bayes rule doesn't have time explicitly. There's always a notion of prediction in Bayes rule. So there is this joint distribution. We are trying to find the best internal representation of the past, which to me means that there's some sort of fuzzy, not necessarily deterministic map, or as Arnold called it, soft map from the past to this internal representation. And this soft map should be such that its ability to predict the future is optimal. And this, when I ask what do you mean by this, what I actually mean by this is that when we have many cycles, we're not operating on one cycle. We have a long sequence of cycles. Even during this minute or seconds of discussion with you, we are running through many cycles like this. And therefore, I can use the fundamental notion of entropy or typicality, if you want. I'm looking for the typical behavior of this cycle. What I mean by typical, this should be very familiar to statistical physicists or information theorists. Some other people are a little bit confused by that, but it's simply a very simple mathematical fact that everything that depends on large random products, tend to concentrate around the typical behavior very quickly, after exponentially fast, such that even if I talk about 10 or 50 or 100 cycles like this, with very high probability, I'm going to see the most typical. In some cases, it's called maximum entropy. In some other cases, it's called minimum information. In this case, it's actually minimum information. So the environment is fixed, and I'm asking what is the typical state of my brain at a given time, and this is going to be completely dominated by some functionals of these probabilities, which are well known in Shannon as mutual information. So this is not because I like mutual information, because this is dictated to you by the law of large numbers. The typical sequence of events is going to optimize to be at the minimum of the mutual information, which is exactly just a simple generalization of the maximum entropy principle. This is the most typical behavior. So of course now we have two quantities, which happen to collide or coincide with this notion of capacity of the two channels that I was talking about. It's not a coincidence, but it's nice to know that this is just a channel, and what the information theorists call channel with side information. Essentially, I have side information due to this feedback channel. This is the environment itself. But otherwise, I'm trying to optimize this channel, meaning try to forget as much as I can about the past without hurting this channel. So maximizing this and minimizing this. And this is the principle that Eli again mentioned, which we called maybe mistakenly many years ago the information bottleneck principle, because I thought about it as some sort of a bottleneck between the future and the past. We're trying to squeeze as little bits as possible without hurting our performance. Okay, so once we know what we do, we just formulate a mathematical problem. We trade between these two things, which means we minimize this subject to constraint on this, or maximize this subject to constraint on this. Doesn't really matter. We put a Lagrange multiplier on one of them and optimize the linear combination of the two. Of course, subject to what? Subject to my perception.
Why not maximize the difference between the two?
Because I know how to work with Lagrange multipliers. That's what I'm supposed to do when I have constraints. I want to minimize the information subject to this constraint. Since Lagrange, more or less, Euler and Lagrange told us that we have to put a multiplier on the constraint and take the sum. Actually, it's different in this case because we want an inequality. We want a positive Lagrange multiplier with the Kuhn-Tucker condition and all that. Never mind. So this is not up to me. I can't take it's the difference if you want, but not the ratio.
No,
the difference is okay, yeah. It's a negative Lagrange multiplier. So I actually think about it as a positive number with the difference. So anyway, this is, surprisingly or not surprisingly, is a solvable, tractable problem. I can explicitly do it, and I can do it without assuming anything, in principle, about the model of the environment. So what I mean by do it, I can actually solve this equation. And I skipped this technical part here, but I can have an explicit closed form, or not analytic in general, solution to what is the distribution, the perception channel that minimizes the perception capacity under a constraint on the value of my actions. Believe me, together with a lot of good people that helped me over the years, and the good students here, we managed to put this framework on a very solid ground now. And of course, things are much simpler and much better behaved when we make some assumptions about the environment. For example, one easy case, which we know how to solve for 6-7 years now, is where the environment is jointly Gaussian. Then everything is analytically tractable, has a single global optimum, and so on. Or in a slightly more general case, where this is an exponential form. Then we know how to do it. There's an explicit form, because then there are exact sufficient statistics that we can exploit and so on. And actually, we now know, Noah is not here, but we have reasoned things. We can generalize it very nicely to what we call using the kernel trick. Those of you know what it is, and many of you know what it is. Essentially, what Bartnik showed us, that you can take anything which is linearly separable in one space, which is essentially equivalent to the Gaussian with an Euclidean margin, and embed it or map it to something which is linearly separable in entirely different spaces in kernels. And actually, you don't have to know the kernel. You don't have to know the embedding explicitly. You can only use the properties of the kernel and essentially repeat the whole thing. And we now know that there is a kernel information bottleneck, which is much more general than the Gaussian one, and has exactly the same tractable analytic structure. It has a global convergence and everything. So this is very nice. We can solve this problem whenever we assume that in some embedded space, things behave like Gaussians. Okay, so that's nice. It's not. I used to apologize about it many times. It's not convex. It's as good as most machine learning algorithms, which means it can be kernelized and then solved efficiently. Okay. Now, just to show you how it looks. So this is a very simple illustration, again, due to Jonathan. Essentially, the answer to this question gives you a curve, which we called the information curve yesterday. And this curve is completely analogous or identical, if you want to the rate distortion function, for those who know what it is. Or actually, it gives you a separation between two regions in this information space, how much information I perceive from the environment versus how much information I need to use. And this boundary is a hard boundary. It's really a phase transition in the sense, in language of physicists. In this phase, there are solutions, and in this phase, there are no solutions. There is no sensory system which will take us above this curve. And this curve is also the one with minimum information, so I can get it by minimizing my perception information. Actually, here it's, I fix this information, then minimize this one. So I get this. This is why this upward concave like this. And the boundary is also the one with the minimum information, and therefore it's also the most typical, or most likely, in some long cycles of behavior. So the boundary is very, very important. And again, Eli mentioned it very briefly. Why we expect the cat to be near the boundary? Because we believe in the large number theorem, or we believe that typical sequences are going to be near the boundary. Okay.
Could you repeat, if I understand well, if you fix in horizontal way, you fix the type of information you need.
Yes.
And so you have the possibility to have many different types of information.
That's right. That's right.
What
are these information precisely?
You want to minimize.
I want to minimize this, but I want to keep the information about the future at some fixed number. The fact that I can have positive information about the future is only because the environment itself is predictable to some extent. Otherwise, I cannot do it because there's a data processing inequality here. Of course, this information cannot be larger than the information that there is in the environment already. Okay. Anyway, so what happens is that when you reduce this, when you put the maximum information available, then you get a deterministic internal representation, which is essentially, in this case, you see it as a diagonal. It's simply the full information about the environment is there. This is the full statistics. Nothing is lost. Nothing is thrown away. But as everybody will tell you, this is impossible. We have too much information around us, so we need to squeeze it. Actually, we simply don't have so I can reduce, let's say, the information that I perceive, my perceptual capacity, the information that I need to store, by a factor of 70%, without losing more than 10% due to this concavity. And so this is exactly the visual information I'm going to throw away. And this point, somewhere like this, where the slope is more or less, this point is determined by what we call the law of diminishing returns. I mean, how much I actually gain by adding a little more complexity to my perception in terms of value, which is translatable to information. So this is the operation point. This is where the intelligence wants to be. This information is essential, and this is what, or vice versa. This is what we can spend money for, and I don't want to be left of this curve. I cannot be. I want to be on this curve. So there's a price for perception, and there's a value for prediction, and I want to balance them. So essentially, this is just a twisted way of thinking about the optimal trade-off between the cost of my sensory perception and the value of my actions. Yes.
Wouldn't that be the same as what I asked? Take the difference between the two. That would be the state where the difference is maximum.
Yes, but okay. I could do any sort of linear transformation. I like to think about it as an upgrade. If you remember, the rate distortion function is actually going down because you want to minimize distortion, but that's trivial. Yes. So question, yeah.
What's the model of the environment in this example?
So here it's a very simple IAD case. This is just an example. The two variables, x is the past is I have 18 numbers, 18 possibilities, and the future has 2, and the distribution is this. Okay. It's trivial. I mean, it's a linear. That's why it's easy to see. This is the joint probability. So the probability of having x0, so then y is deterministically a, and x18, y is deterministically 1, and b, and in between they're just linearly related. So this is just to allow us to follow the illustration, but it's of course not essential. So what you see here are two things. First of all, what is the trade-off? What is my optimal trade-off between past and future information, or the two capacities? What is the complexity of my internal representation? So you see here that my internal representation has a fuzzy 3-state solution in this case. It's again soft as you like. So there are actually many possible values that I have to keep in my representation. I don't keep 3, I keep a whole distribution. But this information has only 1 bit. 1 bit, your immediate association is 1 yes-no question, but actually I can have 1 bit spread over 3 or 10 or whatever internal states. And this is the quality of my prediction. So this is the true prediction, and this is the predicted, the distorted prediction. And you see that, of course, the lower I get on this curve, the less complex is my internal representation, and the less accurate are my predictions. I'm actually starting to lose, especially on the high and low probabilities.
Can you explain again what is in the
The
middle?
middle is some sort of, this is exactly the distribution pt over pt given x. So t has 18 values here, and x has 18 values here. So the fact that it's a full representation of the world, this is not essential, but it's easy to depict it this way. But you see, this is a very low entropy, essentially 1 bit, or even less than a bit. There's essentially 2 clusters here. But this is not essential. It can be dimension reduction. It can be many other ways of thinking about it. It can be distributed over neurons in the brain, and so on and so forth. So essentially what you see here is the higher I go, the more complex my internal representation. When I go to the full information, this is essentially an identity map. But this is not interesting, because then I don't throw anything. And of course, my prediction can be almost perfect, as you can see here. I lose something in my prediction, but I still use a much simpler representation, or I need to perceive and remember in my sensory system much less bits. Okay, I have to run now, because I really want to talk about the topic of this talk. I just want to show you how this looks in general. So this is actually an analytic solution of this type of problem that I mentioned before, the Gaussian and the kernel type of bottleneck, where I know that the distribution is embedded, that there's some high-dimensional space in which we have Gaussian linear separation, and I assume all the assumption of the kernel trick, and then I get a very nice cascade of curves. So you see the optimal curve is the blue one. This is the information curve, because I have a full dimensionality. But if I am restricted to lower dimensions for some reason, then I start with the optimal curve, and then I'm forced to leave it to some suboptimal curve, which is dictated by the dimensionality. Essentially, in every one of these points, I get some eigenvalue of my covariance matrix, or my conditional covariance matrix, to coincide with the level of the noise, with this Lagrange multiplier. And it's exactly the same, for those of you who know some information theory, the effect that we call water filling in calculating the capacity of the Gaussian channel. It's exactly the same phenomena, but what happens here is that the bottleneck in this case, in the Gaussian case, rediscovers or actually slightly generalizes the notion of canonical correlation, which is some extension of PCA that I'm sure a lot of you know. It's a very important algorithm, essentially how to preserve information in one Gaussian variable, which is jointly Gaussian with another Gaussian variable so it's a two-side projection, which is usually implemented very easily by SVD, by singular value decomposition. So essentially everything boils down to SVD in this particular case, including the kernel case. But the kernel just has another kernel in between. So you do an SVD on the kernel, not on the covariance of the kernel instead of the original feature space. But what's really interesting is that you have this cascade of transitions, and every one of them corresponds to a structural phase transition in terms of emergence of another dimension in your representation. Okay. Remember this. I just want to briefly mention something very, very important. I mentioned this, everything depends, crucially, on the amount of information you have in the past about the future. So everything depends on the fact that this feedback channel has a positive capacity. Or in other words, in some simpler way, I can predict something about the future. There is some mutual information in the past about the future of the environment. This is a notion that I mean, Bill Bialik and I, and then Ilya Nemenman did a whole PhD on this almost 10 years ago. We actually thought that this measure, this nice measure, how is the information from the past to the future, depends on the size of the window. Let's say I now look an hour back and an hour into the future, or a minute back and a minute into the future. It must not be symmetric, but I need to get some sort of an extensive quantity. Let's think that I'm thinking a year back, or 2 years back, or 10 years back, how much I need to collect in the past in order to make sense, still have value in the future. So the original insight was that this information, when you extend the window in both directions, grows with time. Of course, it should grow with time. There's more information in large windows than in small windows. But the surprise was that it grows very slowly with time. So this is what we call, it's growing sub-extensively or sublinearly. It doesn't grow linearly with time. This is a big surprise and a very important fact for the notion of our discussion here. This is essentially the reason why we exist, as far as I'm concerned. Why we can cope, if you want, with the enormous complexity of the world around us. Because something else actually grows linearly with the window size, is of course the entropy. So if I look at, you know that the mutual information between these two sides is simply the sum of the two entropies minus the entropy of the sum. It's a very small effect. Sorry? Yes, okay, irrelevant, sorry. There's a calendars vicious. Anyway, so this joint distribution grows, the mutual information, while the entropy of this joint distribution grows linearly with time, because of if it has a constant entropy rate, it's a stochastic process with a constant entropy rate, then we know that the entropy grows linearly with the rate. I mean, linear with time multiplied by the rate. The mutual information is sublinear. What it actually means is that the capacity of this channel saturates. And actually, we know how to calculate it. We know how to calculate it. We can actually estimate analytically, in many cases, this predictive information as a function of the window size. And we know that this is simply the capacity of the channel written in this funny way. For Gaussian processes, for example, for Markov chains, for everything that you really use, graphical models that have Markov conditions and so on, this can be analytically tractable. And it grows, surprisingly, logarithmically with the time rate, not linearly. Which means that the complexity of the events in the past that we really need to remember for our predictive information, for our usage in the future, is a tiny fraction of what is there in the past. It's log T over T, asymptotically.
So this helps for us aging?
Absolutely. We really don't have to remember most of the things that we see. This is a bound. I mean, we know that we cannot have more information than this predictive information. So if you plan ahead, your time is compressed logarithmically. I mean, essentially the resolution of the events in the future and in the past that are relevant that is sparsely, is exponentially or power law sparse. I mean, actually we need to think about the immediate future in very high resolution, then the next day in smaller resolution, and so the more into the future we look, the lower our perception of time and details that we can, in principle, convey and perceive. Actually, more generally, this is true for parametric models, and this is actually the dimensionality of the parameter space, and many of you may know this as the MDL or something similar to this, the dimension of a 2 log n. This is just the stochastic complexity of the process. So it was rediscovered in various contexts as a capacity control, or as a complexity control, or as a model order estimation method in machine learning, due to reasoning and due to many others. In Bayesian analysis, we see exactly the same thing in any parametric model. But luckily, our world is not parametric. There are many, not parametric in the sense of finite number of parameters. The number of parameters actually grow when we investigate or sense the environment more and more closely, and eventually we see details that we didn't see before, and there's always this hierarchy of structure, and this hierarchy of structure means that there are details on every length scale which are important, both in space and in time. So I need to plan ahead, and I need to chunk my events in a way which will allow you to make better and better predictions. So in general, we show that in the non-parametric case, this grows like a sublinear power, which again means that the fraction of relevant events in the future or in the past is infinitely small, and most of it is irrelevant. By the way, this has some mathematical implications. For example, it's easier to estimate the mutual information than the entropy, a lot easier. And we'll come back to this. This is why the whole system works. You don't need to estimate entropy in order to estimate mutual information. Okay, so this part is just essentially repeating what Eli told you yesterday, how we use it. So essentially in Eli's case, we have a sound here, we have prediction of the next sound, and we are trying to guess these two conditional distribution based on this variational principle, minimizing the information in the past subject to information about the future, which in this case is only two sounds, so it's very, very simple, and we can do it analytically essentially and calculate this complexity curve. And what Eli showed you yesterday is that his poor cat is lying somewhere on this curve due to this typicality argument. I don't have to assume anything about it, just assuming that the cat is really exposed to many, many cycles like this. And what we actually find, so we did it actually a little more carefully. We also changed the memory, the window size, and you see when you increase the window size, everything converges to the optimal curve. But for very short windows, we get suboptimal curves. And then we estimated how well this particular model fits the response of the cat, of the neuron in the auditory cortex of the cat to sound, and we found that this nice red spot is where the neurons are in some sense. And then Eli showed you exactly how we know it. I mean, we actually estimate the amount of surprise now. Now, the first time I used the word surprise, that's actually very important to... What I mean by surprise, the average surprise is the log of my subjective probability, the probability that I assign to the next event. Of course, it can be done in the method that Daphna mentioned yesterday in a parametric Bayesian way, but it can be done also without it. And if I just think about my internal representation of the world, Bayesian or not Bayesian, as some sort of a model which infers probabilities, then the log or the minus log of this probability of the future is my surprise for the next event. And minimizing the surprise is just maximizing this capacity. It's the same thing. Simple algebra. So, and it's the log probability, it's not the probability. It's the log probability, again, due to this typicality argument. We want to think to self-average. So we want large sums are much more important than large products, or large products behave like the log average of the sum log. This is, again, exactly the same principle of typicality again and again. So what Eli showed you yesterday is that we can actually explain the behavior of these neurons quite nicely, almost completely. He was not very precise about it, but he didn't have time. This is not a Poisson distribution. As you can actually see yourself, the variance does not increase linearly with the rate, as he said, or the standard deviation does not increase linearly with the rate, actually almost decrease, which means that the story is a little more involved than that, but it still removes more than 50% of the variance. These are individual responses to the sound. Okay, so here is a very strong, to us at least, compelling evidence. We have a hard time convincing referees about it, but it's a very compelling evidence that the brain is actually encoding surprise. Okay, so now I want to go quickly to our project. And how is it related to this? Which actually we didn't write anywhere. So we have, I have more or less 10 minutes. Since Andrea and Rita prepared the ground very nicely for me, I only have to show you how the ideas that we use there are really connected together. And this work is largely done by Simone Calderara. Uri Heimann is sitting there, and Andrea and Rita, of course. So this is really, maybe you don't see it, but to me this is part of a much larger picture of how things are predicted and surprising. And so again, we actually did very simple and systematic sequence of steps that were mentioned. I just want to repeat them again. These are just pictures from our paper. We turned the video sequence into trajectories. And by doing this, we did something which is against the principle that I just mentioned. I'm eliminating time. But we noticed that this is almost essential when you deal with video. I mean, you have to pay somewhere. If you want to compress video, so this embedding, I mean, I want to take video sequences and turn them into something which machine learning can handle. And machine learning is much better in processing discrete, finite number of objects for all sorts of reasons, although it's not essential. So we take cameras, and we use the wonderful tracking systems of Rita and Andrea. We eventually connect and generate trajectories like this. And essentially, this is already some sort of an integration over time. And actually don't explicitly even use the duration itself, although it's there. And then, so we take videos to trajectories. Our goal is really to somehow identify anomalous trajectories. And what do we mean by anomalous trajectories? Those are things like this, where you have a person running around a couple somewhere without an obvious reason. And this is obviously interesting for security reasons. What is it? Why is he doing this? Or something like this, which are the first one was actually pickpocketing. Which one was? One of them was an attempt to take this one.
Take a bag.
To take a bag or something from the person. The other one was an attempt just to listen, or I don't know what, to what they talk. But anyway, this is what we would like to call an anomalous behavior in this type of environment. And the idea is, to me, is how we turn this into a surprising environment, into a surprising event in this rather complicated formalism that I mentioned to you before. Though I think it's not complicated. It's just it's simple when you see the principle. So. Like everything, it looks complicated. If there's no some underlying simple basis, then it's useless. So essentially, the idea was just using a bag of hacks and tricks that just works. So the first thing is really, I don't expect you to read it, but just to remind me what's happening here, is to move. This is an idea that I used in other contexts, and some of you know where before. So we just applied it to essentially taking those trajectories and turn them into graphs. So how do we take them? If we take them into graphs, then we have a bag of tricks with graphs, which are all known as spectral embedding or spectral clustering or spectral analysis of graphs. This is a very nice and very powerful tool and a very robust tool for reasons which are very close to what I mentioned before, because they're essentially a quadratic form that involves the Laplacian of the graph that allows me to do all sorts of spectral analysis, diagonalization, and eigenvalue analysis, and so on and so forth. And it's due to some assumptions about the graph. So the first thing is to take a collection of trajectories and move them into weight on a symmetric graph. Now, this is a bit tricky. So first of all, the first idea that comes to mind is to discretize the space somehow, like a grid like this, and simply sample transitions between adjacent cells in this graph. As you can all see immediately, this is a bad idea, because it's not taking into account the correct statistics of the data in some sense. I mean, in this case, you see trajectories in these cameras, and they're all centered in very non-uniform way in space. So the first idea we use is to sample it in a slightly more sophisticated way, actually very little more sophisticated way. We actually sample the trajectories randomly. Let's say you want to have n or m or k, I don't know what you call it, partitions. So we just sample the trajectories themselves. So in other words, this is a gold rule of machine learning. Let the data decide for you. Never decide for the data if you don't have to. And the data in this case is simply sample the space and generate those Voronoi partitions of the sum. So this immediately generates some sort of a non-uniform grid. And in this non-uniform grid, I get much denser sampling in the dense part of the distribution. This, of course, an old idea from it's very similar to Parson windows and many other things that we used in pattern recognition hundreds of years ago, or 50 years ago, 60 years ago. And essentially, then you get a much more reliable sampling. And then the next step is simply to take this Voronoi sampling of the environment and turn it into a graph again. So here again we use some tricks. And correct me if I'm wrong, by the way, if this was really the version. First of all, so we look at transition between adjacent cells. So how many times there was a graph that actually moved from one cell to another cell. Fortunately, this is a two-dimensional problem. If it were 3 or more, we had slightly more complicated. But there are Voronoi partitions, of course, in higher dimensions. But the notion Voronoi partitions will work in any dimension. But in 2 dimensions, it's very simple. So in 2 dimensions, we can just count the number of transitions in our data from one cell to another cell and symmetrize it, which means essentially we have a time reversal symmetry in our data. So we assume that this trajectory is as surprising as this trajectory. This is I must say that I don't like this assumption because it again, but it's at least I know what I assume. I assume time reversal symmetry, which means that I don't care about the direction of my video, but otherwise time is still there. And then we generate a graph which simply has weights on the edges. The edges are just pairs of cells. So we have k square edges and k to the 4th possible transition, but very few of them are actually seen in our data. So we take this big matrix of symmetric matrix of weights, and then we do the usual, the standard. Where is here? He's not here today. He's not here now. But we use the standard idea of spectral clustering, which is essentially move from the weight to the Laplacian of the weights. Other people here who never heard about it? Anyway, so Laplacian is actually a name coming from after Laplace, and as some of you may know, Laplace did very different things. He did a lot of things, but he actually didn't talk about graph clustering. What he did was essentially this operator known as Laplacian. Most physicists see it first in first year electromagnetism. It's actually the divergence of the gradient of a field. Essentially tell us it's Laplacian, the sum of the squared derivatives in Cartesian space, and it's essentially tells us how much flow, what is the net flow through a cell in the space, how much comes in versus how much comes out. Turns out that this old Laplacian from vector analysis, vector calculus, has a nice graphical realization. If I think about flow on graphs, not flow in real space. And essentially what this Laplacian is telling us, for every node, what is the net flow in and out? If there are no charges there or no source for the flow, then the net flow should be 0, and the Laplacian is 0. And if there are sources or sinks, I mean, the flow is swallowed somewhere, just like charges, positive and negative charges in electromagnetism. You have a non-negative Laplacian. But what is really nice about Laplacian is that it has the natural energy of a graph, which means the sum of the difference square between nodes weighted by the weight on the curve. So if I call this the natural energy, I want adjacent nodes on the graph to have similar values in some sense. If they are strongly connected, then this gives me a nice basis. The eigenvectors of this operator. It's an orthogonal basis on the graph that it's orthogonal because the matrix is symmetric. This Laplacian is symmetric, of course. And this basis is really giving me a nice, exactly like the Fourier basis in Cartesian space. So the Fourier basis is just the eigenvectors of the Laplacian of Cartesian coordinates. The spherical harmonics, for those of you who know, is eigenvectors of Laplacian in spherical coordinates and so on and so forth. So we all know this system. On graphs, this particular eigenvector of Laplacian is a good basis on the node that really give us a way of expanding the different differences between them. So now we can do a very nice trick. And I'm out of time, I know. But I'm also the chairman. It's fine. So now I can use a very simple trick. I essentially filter out, just by doing low-pass filtering on the if I'm telling you low-pass filtering in Fourier space, what it means to most of you, I hope, is that I leave only the frequencies below a certain frequency, okay? Which means I expand my signal in only the lower eigenvalues of my Laplacian. In the graph clustering or graph analysis sense, it's exactly the same thing. I filter the activity by expanding it in the eigenvalues of this Laplacian operator, which is different for every graph. And then I filter it. I do a low-pass filter, which essentially is a noise cleaning process. It's giving me, it's a noise reduction process. That's why it's very useful. So what we do is we take the Laplacian, which is this d minus w, never mind that. It's a very simple matrix, symmetric matrix. Actually has negative eigenvalues, as positive the way it is defined now. We take the eigenvectors of this Laplacian. Actually, we want to low-pass filter it, so we don't take all the eigenvalues. We take only the first k. And how we define this k, it's an art, but essentially we hope that there is some sort of dimension reduction that coincides with, usually there's some sort of a knee in the spectrum, in the eigenvalue. So we cut. And if there's no knee, just use the first 1, 2, 3, 4, whatever dimension that you want to throw your data into, which is exactly like low-pass filtering in signal processing. And then we, together with Uri and others, we investigated all sorts of nets. So mathematics tell us that if we want now a measure of similarity between graphs using this Laplacian embedding, it has to be made out of invariant quantities. So for me as a physicist, this is completely obvious, but mathematicians, they have to convince this is really right. Which means that the whole analysis should not depend on any coordinate transformation of my space. In the graph case, it's not exactly obvious why I want to be independent of a transformation, because I really transform the nodes. But it's clear that if we can find invariant representations, it's better. So actually, there are only two invariant representations of a matrix like this. One of them is the determinant of the Gramian matrix, M transpose M, and the other one is the trace, which is, of course, closely related to the determinant. This is a very nice fact about matrices. So any measure of similarity, now I want to actually measure the similarity of two graphs. One is what I call the normal event, the things that I learn from all the trajectories in space, trained on many, many trajectories. I guess just generate a big matrix like this. It may contain some small fraction of anomalous events, but I don't care. The statistic is going to win. I generate a low-pass matrix like this from the whole data, and then I take a single event, one trajectory, generate its empirical Laplacian, and measure the difference between them. And we use two measures. One is essentially the cosine of an angle, some generalized angle between the subspaces, called also the Grassmann distance. It's the determinant, the square root of the determinant. Never mind, this is a nice measure. The other one, which turned out to be better, is this true? Yeah. The trace matrix, which essentially, as I said, is another invariant, and this is what we actually use. And then the rest is simple. So we take trajectories. What you see here is in the background non-anomalous, or what you call normal trajectories. And then for every one of those trajectories in time, we calculate. So there is a temporal process here. The Laplacian is changing. The empirical Laplacian is changing with time. We can do it, by the way, not only for trajectories. We can do it for communication. We can do it for telephone calls. We can do it for many things. And essentially, you just move in time. And the higher this distance, the more anomalous we are. Or the further away our current Laplacian is from the background Laplacian. And this works like it should. Now, of course, the obvious question is, what is the connection between this and the previous story? Anyway, so there are many examples, and I don't think we should not go into the details here. I'm out of time. Anyway, I just want to tell you how it is connected. So essentially, what we assumed here is something surprisingly similar, or maybe not surprising, to what Daphne said yesterday, but in a slightly different tilt. So we actually have a generative model of normal trajectories. And as you already see, or maybe see, this Laplacian formulation is very closely related to the kernel method. Actually, I think Yair Weiss should be aware of it. Yeah, just can. But
you just waited outside the film. Good prediction.
So I just wonder if really the Laplace embedding community knows that. But there is a very nice connection between the kernel method and Laplace embedding. Now, it's actually some special kind of kernel, which is made out of products of those eigenvalues. So, eigenvectors. So, For all I told you about the kernel bottleneck before that, you see essentially what we are assuming here. We assume that the environment here is acting like a Gaussian process when the kernel is actually moving from time to time. So we actually have this background environment, which is one kernel like this. And what we actually did is using this approximate measure between graphs as a proxy, in my opinion, to the true measure of surprise. Actually, yesterday, Daphne more or less gave you the last piece of this puzzle. She actually showed more or less this scale divergence between the prior models based on the collection of all the trajectories, and the single trajectory is a nice measure of surprise. This is precisely our measure of surprise. As the scale divergence is inverted for some reason, but other than that, it's a very similar measure. This average log likelihood relative to the prior. And that's precisely what we do. And now, because we assume this kernel or Laplacian trick, we can have an explicit, everything boils down to functions, simple functions of the eigenvalues. And in this case, it's either the determinant of the trace, because that's the only invariance we have for Gaussian. Everything depends, again, on the eigenvalues of a big covariance matrix. So everything is very nicely linked together, although we didn't write it in any paper. All right, I think I'll stop here. If you have questions, take 2 minutes for this. Meanwhile, we got a few more people here.
Can you say why it's easier to compute the entropy, the mutual information than the entropy?
Because the mutual information, in this particular context of stationary processes that are moving in time, so it's not just an entropy. It's the mutual information between past and future of a stationary process. So because of this theorem that the mutual information grows sublinearly with the time window, it means that I don't really need to sample the whole space. So the small probability events don't matter. So in order to estimate the entropy, and what really is the big obstacle in entropy estimation, maybe Alex should be here to testify for that, is really that entropy is very strongly affected by low probability events. And therefore, any Monte Carlo method or anything like this will have to sample a lot of things which are totally unaffecting the mutual information, because, as I said, the mutual information is affected by a tiny fraction of the entropy. So essentially, it all goes back to tricks that we have been using since the PhD of Yoram Zinger and Dan Aron, or even before this. I mean, I was using since then, but what we call suffix trees, or essentially compression methods. Essentially, we need to sample only those events which really affect the future. And so we can have a very efficient tree that samples all the past with much less than exponential number of nodes. And this is essentially the answer. So you using some sort of a compression algorithm like Lempel-Ziv or any better version of it, you really, but you don't really compress. I don't want to compress. I want to estimate the mutual information. So I grow the tree not when it's needed for compression, but when it's giving me information about the other part. And as I just showed you or argued, waved my hand for you, this is sub-extensive. This grows, let's say, like log T over T, which means that while a full tree will have T nodes, essentially, and the number of nodes actually be exponential in T, because I have a full tree. The tree that I need in order to estimate mutual information has polynomial number of nodes in time and not exponential number. Now, this can be used as an efficient information estimation, although it's not common knowledge and it's not written anywhere, but believe me. Okay.
In the development of your model about information, you did not make any assumption about the environment. But
no, of course, in order to solve it, you do have to make assumptions.
Yeah. But now let's assume nothing about the environment, only that there are periodic events. Like in life, many things are quasi-periodic.
Or even, we have the day, we have the year.
Yeah.
We have the planets that move periodically, so we have a lot of things because of that, yes.
And then the walking and the heartbeat and so on.
Yeah.
And then, so that will interfere with the extent of the description of the window if there are quasi-periodic events. Okay,
it's a very nice question, but a good answer is not short. So first of all, quasi-periodic event, as you said, I mean, it's a fundamental fact about life, but it's a very highly predictable signal. So let's say I have everything is sitting on a sine wave. This contributes a finite amount to the mutual information, which does not grow too much with time. Essentially, it's just telling you, okay, everything has a periodic component. You're not going to learn anything new by taking 2 samples, 2 periods, 3 periods, 4 periods, 10 periods. So this will extend, the contribution to this is what I call the predictive information, or the feedback capacity of my channel, is very small. It's finite. And actually I'm interested in the sub-extensive, in the thing that grows with time. So this is the formal answer. In actually use it, especially if you have if you are trying to predict things on short terms, I mean day to day or week to week, then of course this periodicity is very important. I don't see those students here, but we actually had a nice project last year here where we were trying to predict the events on what is going to be your next touch on your phone. Which means I want to know, you look at your phone and tell you should call your mother now, or something like this. I mean, because that's what you do every other day on that time of the day, and of course, what the system is trying to learn is precisely to have a very useful menu. You probably want to do one of those things now. Start the navigation system. I don't know what you want, call you and make whatever. Look, so this is very nice because this is strongly built upon periodicity. So I know that every week on Sunday I have a class, and I know that on Monday, whatever. And these things are easily predictable, and of course, but the nice thing is really that I can predict those quote-unquote unpredictable things, because they have some statistical regularity, which is not periodic. And this is really where I invest most of my effort. Other questions? All right, so just to remind you, this is an informal, open for questions kind of workshop, and we really want to stimulate discussion. And if you have anything burning or anything that I said that you don't agree or don't accept or don't believe, we are here until the end of the day, and we have especially this last hour for discussion. All right, so thank you again, and now I put my chair hat and invite the next speaker, which is Ami Weiser. Who is actually going to tell us something not entirely unrelated, although he doesn't know it.